Welcome back to the statics course. In the previous video, you have learned how to determine the magnitude and the direction of two forces with a common point of application that act perpendicularly on the body. The underlying method was actually not overly complicated. However, what if the two forces happen to be no longer perpendicular to each other? Well, so much I can tell you right now. Calculating the magnitude of the resultant is going to be very simple, but getting the direction of the resultant is going to be more tricky. Well, this video is designed to explain step by step how to calculate the magnitude and the direction of two non-perpendicular forces. Let's start with the magnitude since it's going to be quite simple. I have two forces, F1 and F2, and these two forces are no longer perpendicular to each other. In other words, the angle between them is no longer 90 degrees as in the previous video. Instead, the angle is 110 degrees, and I'm denoting that angle as delta. Now, F1 is 15 Newton and F2 is 25 Newton. If you want to calculate the magnitude of the result of these two forces, then you can just use the law of cosines. And the law of cosines states, I'm going to write it down, R, which stands for the magnitude of the resultant, is equal to F1 squared plus F2 squared plus 2 times F1 times F2 times cosine of delta. And you need to take the square root of this whole expression. And that's why it's called the law of cosines, because you need to use a cosine, or take the cosine of the angle delta. Now, I'm going to plug the values that I have given. R is equal to, so F1 is 15 Newton. Squared plus 25 Newton to the square, and remember, you need to square the unit as well, plus 2 times 15 Newton times 25 Newton times cosine of 110 degrees and the square root of this whole thing. Oops. All right. Okay. And I'm going to spare the individual steps. I'm going to write down the result. And the result is 24.36 Newton. So that's the way you compute the magnitude of the resultant if the angle between the forces is between the origins of these two forces. So you see, this orange dot is the common point of application, and the angle between the origins of these two forces is 110 degrees. What if the angle between the two given forces is not between the origins of these two forces, but between their added vectors? In other words, if I add F1 and F2 in form of vectors, and I have the angle between the vectors, what is going to be the magnitude of the resultant? Let me show you what I mean. So, if I add F1 and F2, in form of vectors, and I have an angle between these two force vectors, and that angle I'm going to label as alpha. Graphically, the resultant is going to look like this. Okay? Now, how do I calculate its magnitude if I have given alpha? Well, there are two options in this situation. The first option is to convert from alpha to delta, or you could just plug alpha into a modified version of the law of cosines. By the way, if you convert from alpha to delta, then you have your delta, and then you can simply plug your delta into this formula right here. And if you have alpha, then this formula needs to be modified a little bit. I'm going to show you later how it's done. At this point, let's assume that alpha is 70 degrees. Okay? And let's say that we want to convert from alpha into delta. In that situation, the formula is simply delta equals to 180 degrees minus alpha. Okay, so that's how you perform delta if you have given your alpha, the angle between the two force vectors. And in our situation, delta is equal to 180 degrees minus 70 degrees, and that is equivalent to 110 degrees. So basically the angle that we have given right here. And you might be wondering, why can you use this formula? Well, that's simple. If you construct a parallelogram of these two forces, let me actually do that for a second. Okay, so that's going to be parallel to the force F1, and this one is going to be parallel to the force F2. Okay, and as you can see, this is the angle delta, the same as this one, and this angle is alpha. You know, basically, if you compare the vectors, I mean, they resemble in terms of angle, this one and this one. Now, this angle is alpha as well. And as you know, the sum of all angles in a parallelogram is 360 degrees. So the sum of all angles is 360 degrees. And mathematically, I can express that as 360 degrees is equal to 2 times delta plus 2 times alpha. And if I rearrange this equation, I have 2 delta is equal to 360 degrees minus 2 alpha. And if you divide this equation by 2, then you're going to get delta is equal to 180 degrees minus alpha. Basically the same formula as here. And then if you have your delta, you just plug it into this formula and obtain your magnitude of the resultant. Alternatively, if you want to use the law of cosine in a modified form, then the corresponding formula is going to look like this. It's going to be R is equal to F1 squared plus F2 squared, and this time it's going to be minus 2 times F1 times F2 times the cosine of alpha. Okay, so that's if you want to directly plug alpha into the formula and the other forces. Okay, so in that situation, you're gonna get 70 degrees for alpha, and if you do your math, you're also gonna come up with R is equal to 24.36 Newton. Okay, so once again, if you have the angle between the origins of these two forces, then you just use this version of the law of cosines. And if you have alpha, the angle between the vectors of these two forces, when you add them together, then you can either convert alpha into delta and then plug delta right here, or you can just plug alpha into this version of the law of cosines where you have a minus here instead of a plus. Now, what about the direction or the angle of the resultant? As I announced, it's a little more tricky to calculate it, but it's still a matter of plug and chug. You just need to know what and where to plug. First of all, I have cleaned up a little bit, as you can see. I have erased this information here and summarized it into the conversion formula for delta into alpha and vice versa. And I cleared up here because we need that space to show you how to compute the angle of the resultant. And to do that, you need to utilize the so-called law of sines. The law of sines states that if you have a triangle like this, and you have your corresponding angles, so let me denote this angle as alpha because I did already so on the vector construction here. This is going to be beta, and this one is going to be gamma. And to each angle, there is a respective side or a respective leg. A is going to be at the opposite side of alpha, and the other legs are at the opposite side of their respective angles. So here I have B, and this one is going to be C. And the law of sines states that the ratio of A over the sine of alpha is the same as B over the sine of beta, and that's going to be equivalent to C divided by the sine of gamma. So that's the law of sines expressed mathematically. And what is it good for? Well, if you look at our force construction or our force vectors, let's say that we're looking for the angle between F1 and the resultant force R. And I'm going to denote that angle as beta, analogous to this triangle. So if I'm looking for beta, I can just use this formula and plug the values. Let's start with the angle between F1 and R. So I'm looking for beta, and if you compare this triangle and this triangle, you'll see that R is basically A on this side, and F1 is going to be C, F2 will be represented by B. In this regard, since we're looking for beta and we have alpha, we need to use this portion of the equation, excluding C and gamma. So we just use A over sine of alpha is equal to B over the sine of beta. And since we're looking for beta, we need to rearrange that equation into sine of beta is equal to, let's see, that's gonna be equal to B times the sine of alpha divided by A. And if we apply our forces from this triangle, that's gonna be, let's see, so B is F2 times the sine of alpha, which is given, it's 70 degrees, divided by A. And A in our case is simply the magnitude of the resultant force R. Okay, so let's do the math. Sine of beta is equal to, let's see, B had a magnitude of 25 Newton times the sine of 70 degrees divided by A, and A is simply, sorry, 24.36 Newton as calculated. And if you do the math correctly, you're gonna come up with the sine of beta is equal to 0.964, and this means that your angle beta is gonna be 74.66 degrees. So that's this angle right here. And now the only angle left that we don't know yet is gamma. And to calculate gamma, there are two ways. Well, the first way is more complicated. You just apply this formula, but this time you include C and gamma, or you can simply take advantage of the knowledge that the sum of all angles in a triangle is 180 degrees. So, in other words, and let's use the second method, gamma, the angle between the resultant force and F2, is equal to 180 degrees minus alpha minus beta. Okay, so that basically captures the fact that the sum of all angles in a triangle is 180 degrees. And doing the math gives us 180 degrees minus 70 degrees minus 74.66 degrees. And that's easy to determine, which is, 110 degrees, which comes from 180 degrees minus 70 degrees minus 74.66 degrees, and that is equal to 35.34 degrees. Okay, so that's the way to calculate the angles, alpha, beta, or gamma, depending on what angles are given and what angles you're looking for. Now, here's one important piece of information. If your angle between the forces is between the origins of the forces, in other words, if your given angle is delta, like here, then to calculate the direction of the resultant, you need to convert delta into alpha, as shown here. Alright, so if you have given your delta and you want to calculate the direction of the resultant with respect to either F1 or F2, then you just convert from delta into alpha and then apply the method that I have shown here. Okay, so now you know how to calculate the magnitude and the direction of the resultant when the forces act perpendicularly or non-perpendicularly on the body. Thank you for watching, and see you again.